opportunity every single week. So, how many of you are hoping, how many of you are relying on the answer to the first question for your points? Raise your hand. How many of you are relying on the answer to the second question for your points? It's pretty good. From where I sit, it's about 50-50. The solutions to these will be written up and posted on the course website tonight, as well as the solutions to your homework. Please do look through the solutions to the homework, because I do put some comments in there, make some observations that maybe go a little bit beyond what you might have thought when you were working the homework. For example, that problem where you just do all the matrix multiplication, I do write out a little bit about maybe some ways you could have thought about it that would have simplified it. So it is worthwhile to look at it. The answer to the first question is exactly the answer to the first two questions on your homework. If you didn't figure that out, you really could have just copied down the answers to either of the first two questions. And then the answer to the question on the back is very similar to what you did with time dilation. And we're actually going to do a very similar thing today, but we're going to do it graphically. In the homework and on the quiz, you would have done it sort of with equations. We're going to see it graphically today. Okay, so before I get started, are there any outstanding questions from the last time we were together?
How was your birthday?
My birthday was pretty sweet. My girlfriend took me down to this really cool hotel in Denver. So does anybody know what the Source in Denver is?
No. The Source?
The Source? You know the Source?
It's kind of weird.
It's this really old industrial like brick building where they probably killed a lot of things. And they took the interior of it and they made it into this marketplace where there's restaurants and vendors and everything. And then they built this amazing hotel right next to it, which is 8 stories high and has a restaurant on the top level. But anyway, 16 of the rooms have, in the room, a garage door that opens and your whole room becomes a balcony.
Wow.
That's pretty cool.
It is pretty cool. And the weather was actually nice. So.
Did you get to hang out with your mom?
That didn't work out so good. I ended up not getting to see my mom, and she's not happy. But I'll see her next week. January is rough for me because there's like 5 birthdays in my family in the month of January, so I don't feel particularly special. Anyway, thanks for asking. Let's see. What am I doing? Oh, I'm talking about space-time and stuff. Okay, so we're going to talk today just some little odds and ends about features of special relativity, which are probably different than what you've seen before. And so I can't really say there's a theme other than special relativity. It's the theme of the day. What I want you to do for a moment is to sort of think about how general the context or the tools that we've been developing are. So if you think about a 4-dimensional space-time, and we can label it with CT, X, Y, and Z, what I would like to impress upon you is that, and I think this is where people get a little bit confused when they first see special relativity. They see, space and time are put together in 4-dimensional space-time. And they're like, that's it, that's special relativity. It turns out that's not special relativity in its entirety. It is putting everything together, but there's a little bit more that you have to have in the story. Okay? And so what I'm going to do is I'm going to show you 3 examples of 4-dimensional space-times, all of which are different from each other. Okay? But they all start out ostensibly with that idea. So relativity, which is a statement about the laws of physics being unchanged when you do certain symmetry transformations, is defined, as we've developed in the last couple of lectures, by a set of conditions where we have some transformation matrices, lambdas, and then the condition they have to satisfy is that the transpose of a matrix times the metric of the space-time times a matrix gives us back the metric of the space-time. And then we've spent quite a bit of time looking at the G for special relativity. We talked about what the lambdas are. But let me just kind of review this. So for special relativity, we have that G gets this special name, we call it eta, and in this case the metric is just diagonal, -1, 1, 1, 1. So it's a very simple matrix. You can take that G And you can explore the consequences of this equation by putting in the g. This is what we did last time. And what you're led to is that the lambdas include how many transformations, Madison? How many different sort of independent kinds of lambdas are there?
I don't know.
I'll ask you an easier question. How many different lambdas are there? That's a different question. So what kind of group is described by the transformations in special relativity? Is it continuous or discrete?
Continuous.
So if you have a continuous group, how many transformations does it contain?
Infinite.
Good. So Brad, who is still here, will tell me how many sort of independent kinds of transformations does it include?
6
6, right. And those come in 2 sets of 3. We have 3 whats.
boosts.
We have 3 boosts, which correspond to giving yourself a velocity along either the x, the y, or the z directions, and then 3
Rotations.
rotations. Exactly. Okay? Now, remember the rotations here, they kind of depend on identities that are satisfied by sine and cosine functions, good old trigonometric functions. Whereas last time we explored the boosts, and at least one way to write down the boosts, there's more than one, is to make use of hyperbolic trigonometric functions instead of sine and cosine. And that just takes care of that minus sign that we encounter. And this, of course, gives rise to, the love of special relativity. And the space on which we are working in this context is often denoted M4, where the M stands for Minkowski space. Okay. Now that's what we've been talking about, and now I'm just going to do a slightly different second example. If instead of choosing the metric to be eta, instead if I chose the metric to be the identity, so we literally just had ones down the diagonal, then again we're working in a 4-dimensional space-time, but we're choosing a different metric. We could plug the metric into this. We could get a set of, well, this provides us some conditions. From that, we can extract the lambdas. And in this case, you'll discover that the lambdas include 6 rotations. There are no such thing as boosts in this situation. And one way to kind of distinguish is because the 6 rotations are all making use of sine and cosine. Because you'll notice there's no minus sign you have to worry about. The cosh and the sinh only came in to deal with the minus sign. The space-time on which you're working, if this happens to be your choice of metric, is simply R4. Or that's 4-dimensional Euclidean space. Now, whenever you have considered flat space with like an x and a y coordinate system, this is from back in the days of physics 1, you were working on what's called often R2, just 2-dimensional Euclidean space. So this just happens to be a 4-dimensional version of it. The point that I want to make is this is not special relativity. This is just it's kind of like just a 4-dimensional space. You just happen to be calling one of the coordinates t. But calling something t doesn't make it good or special. Okay? It's actually in the metric itself that something interesting is happening. Okay? So the idea that special relativity is just making space and time together in 4 dimensions is not enough. You've got to have this extra bit of structure. Now I'm going to give you one more example, which is probably going to blow your minds, and that's okay. That's what it's meant to be. In this guy, and this doesn't have a name. This is like, I don't even know what this is. This is like 4D space. I don't know. I don't know what to call it. It's like just there's space. There's not really any time. Okay, in this last case, we're going to have actually a really weird looking metric, which is 1 in the first term and then 0s down the diagonal. And then better still, we're going to have a second metric, which is 0 in the first place and 1's down the diagonal. And then we can ask, what are the sets of transformations which preserve these metrics? And what you discover is that in this space, you get, so the lambdas include, in this case, 3 rotations and 3 boosts. Now, it's not at all obvious why there's both boosts. It might be a little obvious why there's rotations. But what gets even weirder is if you want to give this space a name, well, how many dimensions is it? It's 4. It's not 4-dimensional Minkowski space. It's not 4-dimensional Euclidean space. It's something else. It's actually what's called an R3 bundle over R1.
That's what I was thinking.
Yeah, that's exactly what you were thinking. Okay. And the idea here is that in Minkowski space, if we were to kind of draw a Minkowski space, it would kind of look like 4 basis vectors, sort of orthogonal to each other. And the same would happen here. And in both cases, you're kind of rotating in these 4-dimensional spaces. The rotations look a little bit different here because of the minus sign. This guy, though, it's more like there's a 1-dimensional line, and then at each point on the line is a 3-dimensional vector space. And then the transformations that you can do include rotations at each point in this 3-dimensional vector space, and then transformations which carry you along the R1 as well. So it's a much more complicated space. Okay? You ready?
Yes.
This is the first space-time you ever studied. This is the space-time of Galilean relativity, which is not general relativity,
Well, then why did you write it?
because it's Galilean relativity. This is actually the context in which you were working when you did Physics 1. Okay, the idea of Galilean boosts, where if you have a car and you throw a baseball at the front of the car, you just literally just add the velocities. That is the boost that you find in this geometry. So it's interesting, people think special relativity is a more complicated thing, but secretly, if you really asked yourself, what is the geometry of non-relativistic physics? It's actually a much more complicated geometry, in my opinion. This is very elegant to me. 4 dimensions, and you just rotate between all the coordinates. Okay? All right. So what we're going to do now is we're going to dig a little bit deeper into these 2 cases. I'm not going to have much to say about this at all. And why bother? We're doing relativistic physics here. I'm only going to work with rotations because yes.
So in the one that you just erased,
Yeah.
you have to clear both metrics with every transform?
Yeah.
Okay.
So let's see. Yeah, so I'm only going to talk about this purely rotational case because rotations are something which you've worked with before, and so I'm going to proceed today with a lot of analogy. But there's going to be some points where obviously that different metric is going to change the way the story plays out for relativity, for special relativity compared to just pure rotations. So we've got 2 cases. We have in R, and I'm just going to call this R3. So R3 is just literally it's Euclidean space, 3-dimensional Euclidean space. It's the space you think of when you do X, Y, Z. So don't worry about time in this case. And in R3, you just have rotations, and the rotation matrices satisfy this property. That if you transpose a rotation matrix, multiply it by itself, then you get the identity, which is of course just secret. It's code for the metric is the identity itself. And then we have special relativity in 4 dimensions, where, as we've talked about, the the expression which would help us uncover what the transformations are is that lambda transpose times the metric eta times lambda is equal to eta. Okay? Now, this condition is a mathematical expression which many of you might have seen at some point. This is called an orthogonality condition. And it's an orthogonality condition for matrices. I think you're all comfortable with orthogonality conditions for vectors, them being in some way perpendicular. This is what you mean when you say orthogonal for matrices. And this defines for us what's called O3. That is, it's the set of orthogonal 3x3 matrices. Okay. This is going to also define something like orthogonal, but it's not really O4 because of what I just talked about. O4 would be if you were just working with the metric being the identity in 4 dimensions, but that's not the metric in special relativity. So we have to give this a new name, and we call it affectionately O1, 3. Okay. That 1, 3 just telling us one of those dimensions is a little bit different than the other ones. That's also reflected by the minus sign in the metric. Okay. And now I get to evidence to you one of the most weird things, silly things that these seemingly mature physicists do, and that is to say that the space-time that you're working with when you do special relativity is secretly d equals 1 plus 3. And everybody's like,
You guys can't even add, that's 4.
but we call it 1 plus 3 to distinguish it from d equals 4. Because d equals 4 would mean all those space and time dimensions are treated the same. 1 plus 3 means that one of them time dimension is a little bit different. So if you've ever seen 1 plus 3 or 1 plus 2 or 9 plus 1 or whatever, that's just splitting off the time dimension separate. Okay? Okay, so what we want to do is talk a little bit about these groups, because you have been learning a bit about groups. So this is literally any 3x3 matrix I might write down with real numbers that satisfies this condition, and similarly here. But we want to kind of restrict ourselves to a subset of these. And what we want are, we want transformations that are continuously connected to the identity. So what do I mean by that? Well, when something is continuously connected to the identity, that means that I can start with the identity, and then by taking a sequence of very, very tiny steps, in fact infinitesimal steps, I can build up the transformation, any transformation that is continuously connected to the identity. So for example, a rotation by 90 degrees, I can get to by taking, I can take a bunch of 1-degree rotations and just combine them all together, take 90 of them, or a smaller degree or whatever, and I can eventually get to this, okay? To give you an idea of where that could go wrong, the identity, let's just talk about O3 for a minute. In O3, the identity is just that. Now this can be confusing, so let me pause you. I just wrote a matrix, the identity. We use matrices to represent many things in this class. Right now, I'm talking about 3 different kinds of quantities. And I want to make sure you're all comfortable when I refer to them, because sometimes they might be represented by exactly the same thing. There are vectors, which will have 4 components, that we use these transformations on. Okay, so we take these 4x4 lambdas and we use them to transform the vectors. Okay? The lambdas are transformation matrices. All right? The metric is also a 4x4 matrix, but the metric is not a transformation matrix. You don't write down the metric for a rotation by 90 degrees. The metric's just the metric. It's just this thing that sits there. Okay? So when I write down the identity here, I'm talking about the identity transformation. It just so happens that in this particular example, the metric of the space happens to also be represented by the identity. All of this will become much clearer and less ambiguous when we eventually get to index notation. But for now, we're just kind of labeling things by letters, and then we're writing matrices, and so things can look a little like they're exactly the same thing. So a 90-degree rotation might look like this. With zeros everywhere else. Okay? And the nice thing is, and this is just code for cosine theta minus sine theta, cosine theta. And you can just dial the value of theta from 0 up to 90. You can continuously get there, okay? But if I gave you this matrix, okay, there's two observations you can make about this matrix. First of all, it satisfies this condition. This matrix is an orthogonal matrix. Okay? You can kind of see that. This squared gives you 1, this squared gives you 1, this squared gives you 1. It all works out, the matrix multiplication. However, there is no way that you can get this matrix from this one through a continuous sequence of transformations. In fact, I can show you why. You know, in this situation, what you're doing is you're starting with x, y, and z, and then maybe this is a rotation by 90 degrees in the xy plane, and so what you're ending up with is something like this. You're literally taking this and you're rotating these by 90 degrees. Okay? Here, what this matrix does is if you start off with x, y, and z, it takes you to x minus y, z. Okay? It inverts the y-axis. But I cannot take this and get there through any kind of continuous rotation. Okay? In fact, if you put any odd number of negative signs on the diagonal, then the transformation you're talking about does this. It can't be continuously realized as a rotation. Of course, you could put two negatives on the diagonal, and that's actually okay because all that is a rotation by 180 degrees. And rotating in this plane by 180 reflects the x and the y-axis, and that's where the two minuses come from. But if you've got an odd number of minuses on the diagonal, you're really inverting one coordinate. But the thing is that inversion of that coordinate is not continuously connected to the identity. So what we would like to do is we would like to take these sets of transformations and we would like to get rid of these. These are bad. Bad. They're the fruit of the devil. By the way, you might ask, well, what is really wrong with these? Well, the reason why we want to focus on the continuously connected ones is that, first of all, if you have a set of transformations which are continuous, form a continuous set, then that actually means you can do calculus on the set of transformations. You can like take derivatives. And everything's well defined. And eventually that leads you to this beautiful subject of Lie algebras and Lie groups and so forth, which is very important in lots of physics, in particular in particle physics. The other thing is that when you have continuous transformations, Nether's theorem tells you that you're going to have conserved charges associated with that. Okay? So there's lots of reasons to focus in on the set of continuous transformations. So what we want to do is we want to do something that gets rid of, for example, this guy, but leaves all these in. And what we can do is use the following observation. Let me do this in O3. So if I take this guy and I say, okay, I'm going to take the determinant of each side of this expression. Okay? Gabriel.
Yep,
What is the determinant of the identity?
that's a hard one.
I'm going to ask you the determinant of the other side too.
1.
So this is 1. How does the determinant of a product of matrices break up?
product, or the product of the determinant.
It's the product of the determinants. Okay? If you're not, if these things aren't familiar to you, it's okay, like we don't all carry linear algebra in our heads, and you can always write down a matrix and prove to yourself. But you're not off the hook. How is the determinant of R transpose related to the determinant of R?
They hopefully are the same.
They're actually the same. So this you can actually write as det R squared. Okay? The determinant of the transpose of a matrix is the same as the determinant of the original matrix. Okay, Gabriel, one last time. What is det R?
Plus or minus 1.
It's plus or minus 1. So what we discover is that just by virtue of this defining orthogonality condition, we can conclude that the determinant of any rotation matrix must be plus or minus 1. Which might not be obvious. If you write down some rotation matrices and look at them and do the determinant in your head, you'd be like, oh yeah, the cosine and the sine, they do that. Well, here's the trick. The things we want to keep, what is their determinant?
1.
The things we want to get rid of? Negative 1. So all we have to do is say, I want to consider all of the matrices that satisfy this and have determinant plus 1. And that leads us to O3 with det R equal plus 1 gives us what is called SO3, the special orthogonal group in 3 dimensions. Without any further ado, if we take O1, comma 3, and we play the same game, because we can literally take the determinant of lambda transpose eta lambda equals the determinant of eta. What's the determinant of eta? Dylan? Honors?
Negative 1.
It's negative 1. So if I break this up, well, we actually didn't even need to know. But it is negative 1. And we cancel those off, and again, we end up with the same story. So only picking the elements that have determinant plus 1 gives us the special orthogonal group in 1, comma 3 dimensions. So what I'm trying to get across to you, these are letters and symbols and ideas that you've probably seen before, but you know, why SO3? Like, why not just O3? What's the big deal? The S thing is important because it restricts us to this set that are continuously connected to the identity. And when you just restrict yourself to that set, you get a lot of powerful machinery that automatically applies. It is worth investigating whether those other transformations are valid in nature. And in the language of particle physics, that comes in the guise of what we call C, P, and T, the discrete transformations, but that's separate from like rotations and so forth. Yes?
Is part of the reason that they're such powerful machinery is because those are the groups that like the identity is a generator of? Does that have to do with
It has to do with the fact that you can generate
those groups?
an arbitrary element of this group using infinitesimal generators and then compounding them using something called an exponential map.
Oh, okay.
Yeah, so that's the whole story of Lie algebras and generators of Lie algebras. Okay, so there's one last tidbit in this story, and that is in your homework, you will prove the following, that for any lambda, okay, for any lambda, the upper left element, the lambda 0, 0 element, must square, or sorry, its square must be greater than or equal to 1.
Just lambda 0 or every element within?
Sorry, say it again?
Is it just lambda 0 or every element within?
Sorry, say it one more time?
Is it just lambda 0, 0? Or is it every element?
No, 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 it's just the lambda 0, 0 term. It's just the lambda 0, 0 term. Okay, so if we're considering the identity transformation, like literally, if the lambda that we're doing is the identity, then, okay, what is that element? What is lambda 0, 0 if you happen to be dealing with the identity transformation? It's 1, right? So lambda 0, 0 for lambda equals the identity is 1. Okay? And so if we want to consider a set of transformations continuously connected to the identity, then we need to consider lambda 0, 0s that are greater than or equal to 1. Okay? Notice this condition allows for lambda 0, 0s which are less than -1. Right? Lambda 0, 0 equals -2 would satisfy this. But there's a jump from -1 to +1 for the allowed values of lambda 0, 0 squared. Okay? So this is no man's land. And so we're going to rule these out because this guy right here is the identity and we want everything continuously connected to it. So there's one more refinement of this, and in the end, if we combine this with the condition that lambda 0, 0 is greater than or equal to 1, then this leads us to what we call SO1, 3. I don't know why there's that up arrow, but... And this, in words, is called the proper orthogonal Lorentz Group. And if you ever read, for example, I don't know, like Goldstein's graduate level mechanics text, they go to great lengths to talk about the joys of the proper orthogonal Lorentz Group.
So that word is orthogonal?
Orthogonal, yes.
What's the normal in space and time?
Yeah. No. It's the Lorentz Group. It's the orthogonal is this actual condition right here.
Okay.
Essentially what those transformations do is they avoid allowing you to use a transformation that reverses the direction of time. Okay, so okay, so one more word about the algebra, and I'm going to get to something a little more hands-on. The complete symmetry group of SR is what is called ISO1, 3, and that is the semidirect product of P4 with SO1, 3 up. And this group has 4 plus 3 plus 3 generators. And is also affectionately referred to as the Poincare group.
What is the symbol of it?
So a direct product, if I just wrote an X, that literally means that I could do anything here and it would commute with anything here.
Okay.
Okay? The semidirect product is a slight relaxation of that. The technical words are that, so this is the set of translations. So this is literally just shifting t by just going forward in time, like by 3 seconds. Not boosting or rotating, just literally just translating in time or translating in x or translating in y, translating in z. Like taking your lab and moving it 3 feet to the right. So these are the 4 space-time translations, and then these are all the things we've been talking about, the boosts and the rotations. The semidirect product just means that this is what's called a normal subgroup of the entire group, which means that the set of elements in this group can be conjugated by any element in the group. But you don't need to worry about that. It's just, it's a little bit more general than if that was just a full-on X, where it would literally mean these 2 hunks are almost completely independent in every single way. Yeah.
So I thought the Poincare group was between the 4-dimensional Euclidean space and then just the regular orthogonal, not the special, or the not SO1, but O1.
The Poincare, I mean, you can do, I guess you could do what would be called Euclidean Poincare, but no, Poincare is generally the Lorentz Group with space-time translations. The Poincare group is probably sort of a catch-all term for including the translations with a semidirect product of whatever rotation group you have. There's probably a sense in which that's used for all of those cases, but in special relativity, the particular realization is definitely the Lorentz group and the space-time translations. So, the algebra of SO1, 3 is an interesting one. If I take the commutator of two rotations, it turns out that that gives me a rotation. This is something which you will all see at some point in your quantum mechanics classes, or if you take particle physics or other contexts. But generally speaking, if you take two rotation matrices and you form their commutator, you remember the commutator is defined as R1, R2 minus R2, R1. Then you get back a rotation. If you take the commutator of two boosts, however, you get an interesting result that ends up giving you a rotation. And then if you take the commutations of a rotation and a boost, you get back a boost. So there's definitely some weirdness going on between the boosts and the rotations. So it's a little bit more complicated than what you're used to. Okay, I'm gonna kind of, there's one more point that I was gonna make, but I'm not gonna worry about it. Well, actually, yeah. So SR is defined by the invariance of physical laws under the lambdas. Okay, that is the form of a law that you write down. You say, this is my physics. And again, you could write an action or a Lagrangian, and then you can say, if I use a lambda on everything in my Lagrangian, the Lagrangian should come back looking exactly the same as it started. That's what asymmetry means, okay? But the very important consequence of this is that every quantity that we work with in physics, when you're doing special relativity, everything must be defined in 4 1+3 dimensions. So what do I mean by that? Well, you're already used to the fact that your coordinates become a 4-component coordinate. And you can think of that as a position vector. But then there are other quantities that we talk about in non-relativistic physics. We talk about velocity. Okay? We talk about momentum. We talk about energy. Okay? Those quantities themselves are not 4-dimensional quantities. Velocity has 3 components, x, y, and z. Momentum, 3 components, x, y, and z. Energy only has 1 component. But energy is not a scalar, okay? Not in relativity. So in making everything sort of jive with this idea that special relativity is defined by the symmetries, we are going to have to find 4-dimensional versions of all of these things, which we will eventually do. Okay, and that's going to lead to a lot of very familiar results. Most famously, E equals mc squared. Okay, so that'll be coming down the pike. Okay, so I'm now going to do something a little bit different. So are there any lingering questions about this before I move on? Let's get it out. All right. And all that I'm saying is also the appropriate, context in which you do high-energy particle physics, because in particle physics, everything is typically moving relativistically, so you have to use special relativity. Of course, we're eventually going to develop the machinery of general relativity with curved spaces, so we'll go beyond that, but we just got to get there in steps. So now we're going to do some graphical stuff. And again, we're going to start with results that you're familiar with. because when we start doing the results in special relativity, the answers are going to be so weird that you're going to be like, really? I don't trust you, Flournoy. And that's okay, because I'm going to make you. Okay, so the first thing I want to do is think about a rotation in 2 dimensions. And after your homework, you are all experts at rotations in 2 dimensions. And what I want to do is get you to realize that when we talk about rotations, and here I'm talking about rotations of coordinate systems, we're always going to talk about passive rotations of coordinates. A very useful thing for us to do, which we do a lot, is on the same picture to draw the old coordinates and the new coordinates. And it informs us, like, what did we just do? Okay? So we know that if I rotate by some angle phi, then I get a new x prime axis like so, and I get some new y prime axis. And then that's also shifted from the original y by an angle phi. Okay? And all of this is just happening in good old 2-dimensional real space, nothing weird with a minus sign. Now what I'm about to do is I'm going to do this. I'm going to do this, draw that picture in a really a roundabout way. I'm going to reach between my legs to scratch the back of my head, but for good reason, which you'll understand in a minute. And I know you're all going to go home and do that. So, all right. So first of all, let's actually look at how we do this with a matrix. So from your homework, you should know now that if I want to rotate from the xy to some new x prime y prime, then I can get the x prime y prime from the old xy using a rotation matrix that takes the following form: cosine phi, sine phi, minus sine phi, cosine phi. And then I'm actually going to write out exactly what we get. So this is good old matrix multiplication. So I'm going to do, let me write this in this way: x cosine phi plus y sine phi minus x sine phi plus y cosine phi. Okay, nothing that I'm doing should be wowing you in any way. And then this becomes 2 separate equations, because this is a 2-component thing and this is a 2-component thing, and each of the components must separately be equal. So I can literally write this as follows. Okay? Nothing weird yet. Now I'm going to do something that just really is like, why are you doing that? That's so silly. Okay, here we go. So I am going to pretend that I did not know what x prime and y prime looked like. So I'm going to pretend that I was just given x and y, and then I was given this machinery over here. And I wanted to figure out, how should I draw the x prime and y prime axes? Okay? So what we can do is we can say the following. The x prime axis is where y prime equals Hunter. If you're on the x prime axis, what's the value of y prime?
You're on the x prime axis. It's just 90 degrees from it. So
Well, what's the value of your y prime coordinate if you're on the x prime axis? These are orthogonal. Say it again?
0.
0, yeah. So the x prime axis is where y prime is 0. Similarly, the y prime axis is where x prime equals 0. Are we all in agreement on that? Okay? But we have this machinery. So throwing in machinery, the expression for y prime is minus x sine phi plus y cosine phi. And the formula for x prime is x cosine phi plus y sine phi. Okay? But what I can do is I can take each of these and use them as the equation of a line. Because if you just squint your eyes and look at this thing right here, 0 equals this plus this, This one equation has x and y in it. It's a linear equation. It is a line that you can plot in this coordinate system. And if you put it in standard form by moving this to the other side, what you'll find is that y is equal to tangent phi times x. And if you do the same thing with the second equation, what you'll find in standard form is that y is equal to minus cotangent phi of x. And then, if I just draw those two lines, so tangent phi in this case is a constant. And this is, cotangent phi is of course 1 over tangent phi. And so if I draw the first equation, I'll get something like this. And if I draw the second equation, I'll get something like that. And then I just label them. Okay?
Do it.
I can't, man. At one point in my life I could, but not now.
You,
Okay.
you really? That would have been impressive.
I don't think I want to be that person. Okay, are we all on board? You have to be comfortable with this because what I'm about to do is not intuitive. So are we good?
Yeah.
All right, here we go. What I'm going to do now is, yeah, I'm just going to raise it through. I'm going to draw the exact same story, but this time we are going to do a story where our initial axes are x and ct in two-dimensional Minkowski space. So we're doing 2 dimensions because we don't need to talk about y and z. We can get all the love out of just an x and a t-axis. And then what we want to do is a boost, or as we've affectionately called that, a rotation in the tx plane. Okay? So a rotation in the tx plane, we talked about last time, it takes the c, t, and the x, and it gives us new t prime and x prime coordinates that are related or that can be obtained from the original ones through a boost matrix. And I'm actually going to go back to the Senchen-Kosh form to make the discussion clean. So here we have Kosh phi minus Sench phi minus Sench phi Kosh phi. Remember, the boost matrix is a little weird because the off-diagonals have the same sign. That's not the case for rotations. Sign is minus on one and positive on the other for rotation matrix. And then, of course, it uses hyperbolic functions. Okay, so let's belabor this. If we actually multiply that out and then write 2 separate equations, we find that ct prime is ct cosh phi minus x sinh phi, and x prime is minus ct sinh phi plus x cosh phi. Okay, I'm literally going to follow the exact same steps that we just followed for the more familiar case. The ct prime axis is when x prime equals 0, and the x prime axis is when ct prime equals 0. Can we all agree on that? But now, if we take these expressions, set them equal to 0, and solve for the resulting equations, we find something like this. Whoops, that's a cough. Notice we don't have a minus sign that appears in these two expressions because there's a plus and a minus in each of these. And when you set them to 0 and you move things around, everything comes out positive. One comes out to be cough, one comes out to be, how do we know how to say hand? Anyway. But here's where it gets cool. If I plot these two things on this coordinate system, because after all, these are just equations of lines in t and x, if I plot them, I get something that looks like this. So this effect is sometimes called the scissoring effect of a boost. And there's a lot of weirdness that goes along with it. First and foremost, one of the important things to realize is that the two axes that I just drew, the primed axes, they are orthogonal to each other.
Of course.
They're not orthogonal in the way that you're perceiving them, because I am drawing on a board which is manifestly living in R2. If I could draw these things for you in two-dimensional Minkowski space, then you would go, oh, they're orthogonal. But I can't. I'm trying to force them into R2. I'm representing these things in R2. So to your eyes, they don't look orthogonal. But the way to figure out whether they're orthogonal or not is, of course, to take their inner product and figure out whether it vanishes or not. Okay? Where this gets really, really interesting is that it brings in an issue about how to define lines of constant t or x. So for example, if I start in the original coordinate system and I say, draw a line of constant time, what would I draw? Danielle? What would a line of constant time look like in this picture?
Just be
It would be a horizontal line.
yeah.
Okay? Now I'm going to define that for you in two ways. You ready? A line of constant time could either be a line which is perpendicular to the t-axis or a line which is parallel to the x-axis. Both of those definitions agree, correct? Are they both going to agree here with the t prime and the x prime? No. If you have a line which is perpendicular to ct prime, it's not going to appear parallel to x prime. So the question is when we want to figure out lines of constant time in this picture, or constant t prime, which of these two definitions should we use? Something perpendicular to t or something parallel to x? What do you think? Well, let's just do a vote. Who says parallel to x? Who says perpendicular to t? Okay, so we're split 50-50. Okay? So we don't actually have to guess. We can just trust the math. Okay? A constant ct prime, because we're talking about constant in the t prime, we know what constant t looks like. That's easy. I want to know what constant t prime looks like. A constant line of ct prime is such that this is, of course, constant. But this is always going to be given after a transformation from the original variables by this. So we can take this and we can solve for how we would draw that line. And lo and behold, the equation for a line of constant t prime takes this form. Again, it's just a linear equation. It's got t, it's got x, and that's just some constant. But what's the important feature of that line that you notice? What's the slope of that line? Tanh phi, which is the same as the slope of the x prime axis. So lines of constant time are actually lines which are parallel to the x prime axis. You just have to trust it. Okay? We had to kind of go back and do something that we felt very comfortable about in a more formal way, but that's because in special relativity, where the metric is different, the results are not as intuitive. Okay? Now we immediately see something interesting in this picture. If I start with CT and I take two events, say A and B, that are at the same time in the CT in the TX coordinates, if I do a boost to some new set of coordinates where the lines of constant time are parallel to the x prime axis, what do we notice? They're no longer simultaneous. In the new coordinates, B actually happens before A. So what we just proved graphically was the second homework quiz question, which is show that if two events are distinct, that means they're separated in either space or time. If two events are distinct but happen simultaneously in one reference frame, that's the TX plane, then to a different observer, that could be described by the T prime X prime, they are not simultaneous. Okay? And then the last thing I want to point out is that this simple observation makes us have to go back and rethink one of the most fundamental things we take for granted in all of physics. One of the most fundamental things in all of physics is the notion of a causal structure. Because after all, we have this idea that in physics, stuff happens for a reason. And we need to be able to identify what kind of relationship do we need in order to be able to separate causes and effects. Or if we have something that happened, can we identify the things that could have caused it and then the things that could not have caused it? Okay? In Galilean relativity, which we'll affectionately call GR, maybe we should call it little gr. I don't know.
God.
Gar? Gar. In Gar, I like it capitalized though.
Yeah, I don't know why.
Or hell, let's just go there, man. Guar.
Yeah.
I went to a guar concert.
What's that?
Wow.
Wow.
In the Gar situation, we have absolute time. That means that if two events happen simultaneously to one observer, they're going to happen simultaneously to every other observer. Okay? That's the first thing. The second thing is that in Galilean relativity, there is absolutely no limit. There's no speed limit on how fast objects can move. So I'm just looking for a fancy word. Transport themselves. Can move. Okay? Can be transmitted through space-time. So what we discover is that the causal structure is that cause, T cause, has to be less than T effect. It's a really simple causal structure. The causes have to happen earlier in time than the effects. Okay? And that's something everyone can agree on. Everyone in space-time and Galilean relativity agrees that your parents did the deed before you were born, right? Everybody agrees that A, the cause, precedes the effect B. Everybody agrees on that, okay? In special relativity, we don't have that level of universal agreement. We also have a finite velocity with which information can be, well, I don't know why I'm struggling for this word, propagated, transmitted, Jesus. So in special relativity, we end up having to define the causal structure in a slightly different way. And this is going to bring in an ingredient that many of you have heard of. So the simplest way to illustrate it is just to do a two-dimensional case. Actually, we'll do a 3. We'll do a y-axis because it's more fun than 3. Of course, there's also secretly a z-axis because we live in four-dimensional space-time. And then what we're going to do is we're going to say that there's going to be an event at the origin that I'm going to call A. Okay? And then what we discover is that the event A happens. An event is just a code word for a point in space-time. That's all the word event means. It's like position, but except it's position in space-time, so we call it an event. That event A can influence things in the future, but only at or below the speed of light. All right? Now, the one thing you might have realized is that the limit of this scissoring looks like what? What's the most you can scissor?
Closed.
Yeah, until they're closed. But if you're closed, then you're talking about a line in the CT plane that looks like that. Okay? But that's a line that satisfies that. Okay. So a 45-degree line is actually the line upon which light propagates. And this would be boosting to the speed of light, although we can't technically boost to the exact speed of light. So what we discover is in these space-time pictures, a 45-degree line in a TX or TY plane is going to define for us a light surface. And then if we just kind of think about the fact that light goes out in all directions, then this gets rotated into what is typically called a light cone. Where the idea is, now pay attention, things that you can influence would have to have a delta x over delta t which is less than c. Okay? So that means we're looking at a c delta t over delta x which is greater than 1. So we're talking about the things that you can influence are things within this light cone. So the causal structure in special relativity is that A can cause B for this particular example. And A can cause anything inside of that light cone. That's called the future light cone of A. If we were to ask what could cause A, then what we need to do is construct the past light cone of A, which is again created by lines of slope -1. And then what we discover is that any event in the past light cone can cause event A, and then transitively C can cause B. Because if C can cause A and A can cause B, then C can cause B. Okay? Where it gets weird is if we draw some poor little event out here. Actually, let's do this. Can D cause A? Can D be caused by A? No. So this space-time event D is causally disconnected from A. A can't cause it, and D can't cause A. So this is the importance of these light cones. And it's important because every event has its own set of light cones. So I could have drawn light cones for C, I could have drawn light cones for B, and I would have drawn different light cones. Okay, so this picture is just the light cones for A. And what it tells me is anything that could have caused A, that A can cause, and then everything outside is causally disconnected from A. Now notice, is D causally disconnected from C? Well, if I drew the 45-degree line from C, it's looking like D is causally disconnected from C. Okay? But there are certainly things in the past of A that are causally connected to D. So we really want to take one event at a time, draw the light cones for that event. So in this case, all of this is based on the event A. And then we use the light cones to determine causal relations. Go ahead and ask your questions. I'm just going to write this on the board. Is
So
causality.
does that mean that like an event D can cause something in A's past that would then be able to affect A? Even though they're like not directly linked but indirectly?
Nope. You can try and draw the picture and see if you can get it to work and it won't.
It's all 45-degree lines.
Yeah, you'll see. Like, draw a couple of examples. Remember, light is 45 degrees. You don't have to do this with a CT, X, and Y. You can just forget the Y and just draw like light triangles. It makes the pictures a lot easier. But you'll immediately convince yourself. Because otherwise, if you could do that, then by the transitivity of causality, you could argue that D could cause A. But it can't. And it's all built in there. Okay? So we unfortunately, in special relativity, have to give up this simple causal structure that just cause precedes effect. And instead we have to focus on light cones. All right? It's not that terrible of a trade-off, but it's the reason why light cones play such an important role in all of relativity, including general relativity, because among other things, if this event is your birth, okay, A for Alex, awesome, Adria, almighty. If this is your birth, are you ready for this? Your experience of the universe is confined to your future light cone. That's the only part of the universe you will ever experience. Now that's a space-time region, not just a spatial region. But when we talk about where things, and I'm going to hint at something that you're expecting in this class, when we talk about where things can go and where things can't go, or where things can go but can't get back from, light cones are going to play an integral role in figuring out those details. Adria.
So you said delta x density has to be less than c. Can it be like light-like, where b would be on the 45-degree line?
Yeah, so the idea there is that an event here, like we could call this event K. So A could cause K, but it would have to have caused it through the transmission of light. But it's possible. If you just get ever so slightly off, no, can't do it. Okay, all right, that's it for today. We'll meet again next time. Remember, all the notes from the lecture get posted on the website, as do the solutions to the homework, as do the solutions to the quiz. Yes. Did you miss the discussion? We already talked about this.
Oh, maybe I did. I don't know.
Yeah.
I'm super out of the
I was supposed to bring it up during the quiz. I didn't get it wrong.
Burgers just
What do you say during the quiz?
When you said, oh, I think these things like... Oh, I think I kind of know what you're talking about. I don't have the answer.